Hello everyone, our topic is hand gesture recognition with STA-GCN, two-stream graph convolutional network with spatial-temporal attention. Here's the outline of my presentation. Problem introduction. Vision-based hand gesture recognition has been widely used in virtual reality and augmented reality. With more low-cost depth cameras available, such as RealSense and LeapMotion, the hand joints can be recovered from RGB or RGB depth images easily. Thus, skeleton-based methods have become the major hand gesture recognition pipeline. Compared with RGB images, hand skeleton joints provide more compact features, and graph convolutional network is more suitable for processing data with irregular structure like skeleton. That's why we focused on skeleton-based gesture recognition using GCM. The limitations of former methods are also our challenges. Early methods extract handcrafted features from skeleton sequences. These handcrafted features cannot effectively model the spatial and temporal information. Later, several deep learning-based work which feed hand skeleton sequences into LSTM or CNN networks were proposed. However, these methods did not exploit the spatial connections among joints in each frame and temporal connections between joints in neighboring frames well. The spatial-temporal graph convolutional neural network has been successfully used in skeleton-based human action recognition. These work often use a fixed graph of hand skeleton on spatial dimension and other fixed graph on the temporal dimension, which may not be optimal for gesture recognition. In addition, these STA-GCN methods only use the raw joint coordinates as input and could not capture the motion features such as trajectory. Our key ideas can be concluded as follows. We constructed a dynamic graph using a spatial-temporal graph attention which can be well adapted to different actions. Then, in order to encode hand gestures with multi-scale temporal features, we adopt the temporal pyramid pooling layer. Not only did we use the original joint coordinates, but also skeleton joint offsets between different frames as input for motion stream. This can be better capture hand movement. Related existing hand gesture recognition methods can be divided into two categories: handcrafted feature-based methods and deep learning-based methods. Handcrafted feature-based methods encode the hand skeleton joint sequences into features manually designed for specific problems, while deep learning-based methods first encode the skeleton sequences into feature vectors, and then feed them into RNN or CNN to extract spatial temporal features. However, these methods do not effectively exploit the spatial temporal context of joints, such as the connections between hand joints in one frame and the connections of one single joint across different frames. Inspired by the spatial-temporal graph convolutional network, several work also explored STGCN for hand gesture recognition. They encoded joint sequences into skeleton graph and used GCN to extract features for gesture recognition. These work neither directly modeled motion features nor used dynamic graph to enhance the representation capabilities of the network. 2S AGCN used dynamic graph for spatial dimension, but still used fixed graph for temporal dimension. Now it comes to our algorithm detail. We adopted two-stream architecture for skeleton-based hand gesture recognition, which uses pose stream and motion stream as input. For both streams, we use the same network structure. We first initialized the skeleton graph. Then we use spatial-temporal graph convolution network with both spatial attention and temporal attention to extract the features. In order to encode hand gestures with multi-scale temporal features, we adopt the temporal pyramid pooling layer. Finally, we feed the feature of pose stream and motion stream into fully connected layer, fuse the features, and feed to softmax layer for prediction. Here's a detailed introduction for a proposed method. The figure illustrates our graph initialization. We initialize spatial edge, temporal edge, and self-connection edge of the graph. The spatial edges connect different joints in the same frame. The temporal edges connect the same joints in adjacent frames. The self-connection edges connect the node itself. After initialization for the Gest graph, we adopt multiple layers of spatial-temporal graph convolution to extract high-level features. The skeleton graph used in graph convolution consists of spatial graph and temporal graph. To implement the spatial-temporal graph convolution in the spatial dimension, the propagation rule can be formulated as equation 1, where AS is the normalized adjacent matrix of the spatial graph. The graph convolution of the temporal dimension is similar to that of the spatial dimension. The propagation rule can be formulated as equation 2. The input of temporal graph comes from the output of the spatial graph, where AT is the normalized adjacent matrix of the temporal graph. Spatial attention module as attention mechanism on the basis of spatial graph convolution. The attention mechanism can estimate the connection strength of hand joints that are more suitable for hand gesture recognition. We follow 2S AGCN to reformulate the propagation rule in the equation. The spatial adjacent matrix AS is built upon the sum of 3 matrices. AS1 is original spatial adjacent matrix. AS2 is spatial adjacent matrix learned from data. AS3 is spatial adjacent matrix learned using spatial attention. Motivated by this spatial attention module, we intended it to the temporal dimension. Similarly, 3 matrices AT1, AT2, and AT3 were used to compute the temporal adjacent matrices. The figure illustrates 2 proposed temporal graph attention modules. Figure A shows the vanilla temporal attention layer, and Figure B shows the temporal attention layer with dimension reduction in time dimension. The vanilla temporal dimension layer contains more parameters than the temporal attention layer with dimension reduction. In order to achieve good balance of network ability and total parameters of the network, we used different attention modules in different layers of our network. When trying to extract effective features for the input hand skeleton joint sequences, we applied temporal pyramid to module hand gesture more effectively by fusing multiple scaled features in temporal dimension. The figure illustrates our temporal pyramid pooling layer. We adopt 2 levels of feature pooling. At the first level, we apply average pooling to the features. At the second level, we divide the feature into several segments of same length and conduct average pooling on each segment. Then, we get a fixed length feature by concatenating pooled features of 2 levels. Compared to global average pooling, temporal pyramid pooling can more effectively extract temporal features of actions conducted in various speed, which enhanced the network's performance. In this picture, we present again the overall structure of our network. Our 2-stream graph convolutional network adopts pose stream and motion stream with the same network architecture. For the motion stream, we adopt the skeleton joint offsets as input. Here's the experiment result of our method. In our experiment, we used DHG dataset and Shrek 2017 dataset to evaluate our method. Compared with DHG dataset that labels keyframes for videos, Shrek dataset only contains raw videos captured by the camera that makes it more difficult for hand gesture recognition. To evaluate the performance of our method, we used 2 standard metrics. For DHG, models are evaluated by using the leave one subject out cross-validation strategy. In each experiment, 19 subjects are used for training and 1 subject is used for testing. For Shrek 2017, the videos have been divided into 1,960 training videos and 840 testing videos. We report the accuracy of 14 gestures and the accuracy of 28 gestures for both datasets. We compare the performance of our method with state-of-the-art methods. The left table compared performance on Shrek 2017 dataset and the right for DHG dataset. Our method achieved competitive results for both datasets. To further understand the effect of each component of our network, we conduct several ablation studies. The table shows the recognition accuracy using different spatial adjacent matrix on Shrek 2017 dataset. We observe that our method using the adjacent matrix AS1 plus AS2 plus AS3 worked better than using the original adjacent matrix AS1. This suggests that the adoption of graph attention layer promotes the effectiveness of our network. We evaluate the performance using other adjacent matrices and find they all perform worse than that with the adjacent matrix AS1 plus AS2 plus AS3. Therefore, we choose to use it as the spatial adjacent matrix for graph convolution. Similarly, our method using the proposed adjacent matrix worked better than the original adjacent matrix AT1. This demonstrates that our temporal graph attention layer is effective. We evaluate the performance using other adjacent matrices. They all perform worse because they lack the original temporal connections between the adjacent frames. In order to evaluate the effect of two-stream fusion, we compared pose stream, motion stream, and two streams. The first table demonstrates that the two-stream architecture can best exploit both pose and movement information. In order to evaluate the effect of our temporal pyramid pooling, we conduct comparison using the temporal pyramid pooling layer with the alternative global average pooling layer. The second table shows that the temporal pyramid pooling layer is better. To verify whether the spatial and temporal attention layers are useful, we conduct experiments with different attention settings. The first table shows the recognition accuracy using different attention modules. Baselines means we use the same network architecture of our full model and use the original propagation rule for spatial and temporal dimensions. The results show that both the spatial attention and our temporal attention are effective. In order to investigate the effect of other types of second stream, we compare the performance of our method with our motion stream and the bone stream used in 2S AGCN. The second table shows that our motion stream is better. The possible reason could be that bone stream overlooks the temporal movement of joints, while most types of hand gestures are related to such movements. To illustrate the effectiveness of our proposed temporal attention, we conducted a visualization analysis on temporal attention. The figure shows temporal attention of the gesture shake. Figure A and Figure D shows temporal attention matrices of the first and fifth STA-GCN block. Since we sampled 64 frames from all videos, temporal attention matrices are of the size 64 multiplies 64. From figure A, we can see that frame 12 and frame 40 have strong connection with the other frames. Frame B and frame C is depth images of frame 12 and frame 40, respectively. From figure D, we can see that frame 1, frame 24, and frame 60 have strong connection with the other frames. Figure E to figure G is the depth images of frame 1, frame 24, and frame 60, respectively. These images in frame B and C are both hands moving to the right, and the images in frame E to G are all hand moving to the left. we noticed that hand movements to right and left are keyframes related to the gesture shake, so our temporal attention layer is effective. Here are conclusions and discussion. In this work, we propose a new neural network architecture for hand gesture recognition, a two-stream graph convolutional network with spatial-temporal attention. We adopt a two-stream architecture to model the pose feature and motion feature of hand gesture. For each stream, we encoded the input as a graph, designed a new temporal graph attention module, and also used a spatial graph attention module to construct dynamic skeleton graph. In order to extract multiple scale temporal features, we used temporal pyramid pooling layer. Experiments on two main benchmark datasets demonstrate that our method can achieve competitive performance. Although our method is designed for hand gesture recognition, it can also inspire related researches that can be modeled as spatial temporal graph. Thank you.